Welcome to Shanti-Peace for Mathematics. Have a good day to you, all of you. So in my previous videos, we have talked about the necessary and sufficient conditions for differentiability, which tells you that if f is differentiable, if and only if you can represent your f, it is of the form u plus iv, then its first order partial derivatives of u and v, that is ux, uy, vx, vy, are exist and continuous at z0. If you want to say it is differentiable at z0, this is the first condition. The second condition is the CR equations are satisfied. What is CR equation? It is known as the Cauchy-Riemann equations, and they are nothing but the ux is equal to vy and uy is equal to minus vx. Also, we have converted this CR equation into the polar form into the previous lecture. We also talked about if you drop this condition 1 into the necessary condition, then the function is not differentiable, that we have talked. So both these conditions are required to make a function is differentiable. Now we are ready to introduce a very important concept of complex analysis. It's known as the analytic function. And this class of function is used in everywhere when we are discussing complex analysis function. So what is the definition of this function? It tells that a function f of the complex variable z is analytic at a point z0 if it has a derivative at each point in some neighborhood of z0. So it says that the function is analytic, it has to be differentiable into some neighborhood of z. So there is a point z0, in some neighborhood of this z0, in all these points inside this neighborhood the function is differentiable, then we can say that the function is analytic at this point z0. A function is analytic in the open set if its derivative is exist in every point in that set. So if you want to say a function f which is defined from d to c, and this d is open set, and if you want to say f is analytic on d, that means f is analytic at every point on d. If the set d is not open, then it is understood that there exists some set S in which inside d on which the function is differentiable, and so it is analytic. Let us note about some remarks of a function. Since this analytic functions are much stronger than the derivative, and it also depends the derivative of a function, so we can say that all the results we have discussed about the differentiability we can extend for analytic function also. Necessary and sufficient condition for differentiability that we have talked, we can also talk for analytic function. So if you want to say a function f is analytic at point z0 if and only if the first order partial derivatives of u and v, where u and v are nothing but the real and imaginary component of this function, are exist and continuous in some neighborhood of z0. And second one, we can say that CR equations are satisfied in this neighborhood. So in whatever the neighborhood of there a function first order partial derivatives are exist, in that neighborhood CR equations are satisfied. So now what we have is, if you want to check the function is analytic or not, you have to do the two things. You have to check whether the first order partial derivatives are exist and they are continuous in the some neighborhood of z0, and also you have to check that CR equations are satisfied at that. For example, if I consider this example, prove that f of z equal to z square is analytic everywhere. So to do this, just first of all you have to calculate what is the real and imaginary part of this function. So if I write down this is as x plus iy whole square, that I can write as x square minus y square plus 2ixy. So therefore you will have u of xy, that is the real part, is x square minus y square, and v of xy will be 2xy. Now we have to verify whether the first order partial derivative exists or not. Since these are the polynomial in terms of x and y, so it is obviously differentiable, partially differentiable functions. So we can say that ux will be 2x, uy will be minus 2y, vx is 2y, and vy is 2x. So the first order partial derivatives are continuous because it is also again a function which are polynomial functions, all of them. So they are continuous, and also we can note that ux is nothing but the vy and vx is nothing but the minus of uy. So the CR equations are also satisfied. So we can say that the first order partial derivatives ux, uy, vx and vy are continuous and everywhere, continuous everywhere, and they satisfy CR equations everywhere. So therefore f is differentiable everywhere and therefore f is analytic everywhere. So that completes the solution for this example. Let's talk about the next example. Prove that f of z equal to 1 upon z is analytic at each non-zero point in the finite plane. So this problem can be done in two ways. You can convert this function, its real and imaginary part, in the Cartesian coordinates. If you can write down 1 upon z x plus iy, and if you multiply and divide by x minus iy here, so that can be written as x minus iy upon x square plus y square. So its real part will be x upon x square plus y square and imaginary part will be minus y upon x square plus y square. So hence you can do it by finding its partial derivatives of u and v, and you can go further. That will be more calculative because you have to apply the division rule to calculate the derivative of this quantity. The better way is to convert this function f of z into the polar coordinates, that is r e power I theta. So that I can write as 1 upon r e power minus I theta, and then by Euler's formula we can write this is cos theta minus I sin theta. So you will have u of r theta, which is in polar coordinates, that is 1 upon r cos theta. V of r theta is minus 1 upon r sin theta. Now these are the trigonometric functions and the denominator is a polynomial in R, so that's why they are continuous. So we can say that the first order partial derivatives exist. What we can find out as ur equal to minus 1 upon r square cos theta, u theta is minus 1 upon r sin theta, vr is minus plus 1 upon r square sin theta, and v theta will be minus 1 upon r cos theta. So we can note that this first order partial derivatives, that is ur, u theta, vr, v theta, are continuous everywhere except z not equal to 0, because otherwise the polar form we cannot write down for 0 point. And you just note that what is ur, it is minus 1 upon r square cos theta, that I can write as 1 upon r minus 1 upon r cos theta, and this minus 1 upon r cos theta we can have it is v theta, so that is 1 upon r v theta, and vr we can write as minus 1 upon r sin theta, as you can see here, that is plus 1 upon r sin theta, so that is 1 upon r, I may write this is minus of minus 1 upon r sin theta, and so we can have minus 1 upon r, and minus 1 upon r sin theta is, you know, it is u theta, so that's why it is u theta, and so you have ur is equal to 1 upon r v theta, and vr is equal to minus 1 upon r u theta. We can say that CR equations are satisfied for all z not equal to 0. So therefore the first order partial derivatives that exist and CR equations are satisfied for all non-zero z. We can say that f is differentiable at z not equal to 0, and hence f is analytic at z is not equal to 0. So that's completes the solution for this example also. Let's talk about the next example. If I consider the f of z is equal to mod z. So mod z square is nothing but the x plus I y, its modulus square, which I can write as x square plus y square, and the imaginary part is not that there, therefore I can write it is plus 0i. So your real part of this function is x square plus y square, and imaginary part of this function is 0. So you will have ux, which is 2x, uy will be 2y, vx is 0 and vy is 0. And so you note that this ux is equal to, if this function will be analytic, so it has to be satisfy CR equation. So we need to find out where the function is analytic. Obviously ux is not equal to vx in general, so we need to find out where. So if ux is equal to vy, that implies 2x is equal to 0, that implies x is equal to 0. So that means this condition is satisfied if x is 0, and the another condition, that is uy equal to minus vx, is satisfied if y is 0. So both these conditions are satisfied if z is 0. So ux is equal to uy and vx is equal to minus uy only at 0, 0. They are true, otherwise it is not true. So that means what we can say is function f is differentiable only at z equal to 0, otherwise it is not differentiable. And what is the definition of analytic function says? It says that at the point, there is a point z0, if you want to say the function is analytic at that point, it has to be differentiable in the neighborhood of that point, in some neighborhood of that point. And here what is the situation is, the function is only differentiable at 0. So at this point 0, 0 point, the function is differentiable. All other points are there where the function is not differentiable. So what we can say is f is not analytic everywhere. So this function f of z is equal to mod z square is not analytic at any point. Now this example also tells me something regarding the generalization of this problem, that is, if you have a function f of z which is a complex valued function, it only have the real component and its imaginary component is 0. For example, it is of the form u of xy plus I is 0. So it is a real valued function. If it is given to you, then obviously you will have ux is 0 and ui is 0 if you want a CR equation to satisfy. And ux is 0 means u is independent of x and u is only functions of x and y. Vuy means u is independent of y. That means both this situation will tells you that u is independent of x and y, and u is only function of x and y, so therefore u is constant, and hence you will have f is constant. So what is the meaning of this discussion? It says we can write as a note that if you have a real valued function which is analytic, it has to be a constant function. A real function of complex variable are nowhere analytic unless these are constant. For example, mod z square, we have done this example, real part of z, imaginary part of z, only mod z is there. These are the functions which are real valued functions. Since they are not constant, they are not analytic anywhere. Let's have the new example, so that the function f of z is equal to 1 upon z minus 1 is analytic at z is equal to 1 plus. Here first of all you have to calculate the real and imaginary part of this function, and we have to show that the first order partial derivatives of its real component ux, uy and its imaginary component vx, vy are exist and they are continuous in the some neighborhood of this 1 plus I, and also CR equations are satisfied in that. So let us calculate the real and imaginary part of this. If you can write down this z minus 1 as x plus iy minus 1, and if I multiply and divide it by x minus 1 minus iy upon x minus 1 minus iy, finally what you will have is x minus 1 minus iy upon x minus 1 square plus y square. So therefore your real component u of xy is x minus 1 upon x minus 1 square plus y square, and v of xy is minus y upon x minus 1 square plus y. So let us calculate its partial derivatives. So you know that this is of the form px upon qx, so you have to apply the derivative rule, so that is x minus 1 square plus y square whole square, and x minus 1 square plus y square as it is. The derivative of x minus 1 is 1 minus x minus 1, and the derivative of x, that is this quantity x minus 1 square plus y square, is 2 into x minus 1. So if you simplify this quantity, you will have it is y square minus x minus 1 square upon x minus 1 square plus y square whole square, and uy in the similar manner, since this is independent of y, the derivative of 1 upon z is minus 1 upon z square, so it is x minus 1 upon x minus 1 square plus y square whole square minus. Now let us calculate what is vx. V is this function, so here the numerator is independent of x, so that's why it is minus minus become plus y upon x minus 1 square plus y square whole square into derivative of this quantity with respect to x, that is 2x minus 1. Here is also, I forgot that the derivative of this quantity is 2y. And what is vy? Here the product rule is applied, that is this is a function of y, this is also a function of y, so you will have x minus 1 square plus y square whole square, x minus 1 square plus y square as it is. The derivative of minus y is minus 1 minus minus plus y, the derivative of y square is 2y. So if you simplify this, you will have it is minus of x minus 1 square plus y square upon x minus 1 square plus y square whole square. And you should note that ux is same as vy, so I can write down ux is equal to vy and uy is equal to minus of vx, because it is a minus sign is here. What we can say, and this you should note this ux, uy, vx and vy are continuous function except this point, that is 1, 0 point. Except this point they are continuous. So what is the situation? Here it is a 1, 0 point, and we need to prove that the function is analytic at the point 1, 1, that is 1 plus I, it is given to you. So we have to prove that it is analytic at the point 1, 1. So you just see that in the neighborhood of this, if you choose any one of the neighborhoods, so I may take the neighborhood as with the length 1 by 2 or radius is 1 by 2. So I can write down ux, uy, vx, vy are continuous in the neighborhood, that is all z such that mod z minus 1 plus I less than 1 by 2. So in this neighborhood it is continuous, because this is all of them are of the form p of xy upon q of xy, and they both of them are polynomial. P of x is polynomial, q of x is polynomial. So this function is continuous except q of xy is non-zero. So hence we can say that on this neighborhood it is continuous. You may take as 1 also, but not bigger than 1. Instead of 1 by 2 you may take it as 1, but not bigger than 1, because otherwise this 1, 0 point is inside the neighborhood. And the CR equations are also satisfied on this, that is ux is equal to vy and uy equal to minus vx on this neighborhood, that is all z such that mod z 1 plus I less than 1 by 2. So hence we can say that the function is analytic at the point, therefore f is analytic at 1 plus. That's completed the solution of this example. Now let us have some remarks of further. For differentiable function, we have talked about the sum of two differentiable functions is differentiable, product of two differentiable function is differentiable, and the quotient of two differentiable function is differentiable. That we can have extend that result for analytic function. What we can say is, if f and g are analytic at z0, then you can have a, that is f plus g is analytic at z0. Second, f minus g is also analytic at minus 0. F into g is analytic at z0. Third one, we can say it is f upon g is also analytic at z0 if g is non-zero. So that we can say. The second remark we can say is the composition of a two analytic function is also analytic, because we have discussed the result about the composition of a two differentiable function is differentiable. If you have f of z is analytic on a domain D such that f of D is a subset of D1, and a g of z is analytic in a domain D1, then its composition, that is g of f, is analytic in D1. So that's also we can say, because the result is true for differentiable function. So in general it is true for analytic function, to generalize that. Next definition, that is very important definition, it's called the entire function. So word itself suggests entire means it has to be true for every complex number. So if you want to say a function is entire, it has to be analytic everywhere for any complex number z. So entire function is a function that is analytic at each point in the entire finite plane or complex plane. For example, any polynomial you will consider, p of z is an entire function, e power z, that is a exponential function, is entire function, sin z is an entire function. Next definition is a singular point. Here is also word suggests singular, so that means it is alone. So function is not analytic at that point, but it has to be analytic in the neighborhood of that point. Then a function, it's called the entire, that point is called the singular point of the function f, or we can say it is a singularity of that point. So if a function f fails to be analytic at a point z0, but it is analytic at some point in every neighborhood of z0, then z0 it's called a singular point, or we can say it is singularity of f. For example, if I consider f of z is equal to 1 upon z, then this function is analytic except z is equal to 0. So z is equal to 0 is singular point for this function. Let's have the another example. For example, f of z is equal to z cube plus 3 upon z square minus 2z plus 2 into z minus 3. So this function is also of the form p of z upon q of z, and you know that the polynomials are already analytic, and we have seen that the quotient of two analytic function is analytic except q of z is non-zero. So where this q of z is 0, that is z square plus 2z plus 2, if I consider this two quantity as a 0, that will imply z is 3, or z square minus 2z plus 2 equal to 0, and z square minus 2z plus 2 equal to 0 gives you z is equal to 1 plus or minus I by minus b square minus 4ac upon 2i if we calculate. So therefore the singularity of this function, the second function, are 3, 1 plus I and 1 minus I are the singularity of this. Singular point is the function fails to be analytic at that point, but it has to be analytic in every neighborhood of that for some points. Now we'll talk about the next concept, that is called, you know that the derivative of the function f of x is 0 if f is a real function, you know that then function is constant. Here we have, there is a theorem we consider. It says that if f is analytic on D and f dash of z equal to 0 for every z in D, then f is constant on D, where D is a domain. So to prove this, since it is given that f is analytic and differentiable, so f dash of z, and in the previous lecture we have seen that the derivative of the function can be calculated as ux plus ivx. So due to that we can say it is ux plus ivx equal to 0. So that will imply ux is 0 and vx is 0, and since f is analytic, so therefore ux is equal to vy will gives you 0, and vx is equal to minus uy, which is also 0 because of CR equation. CR equations are satisfied due to analyticity. So therefore we can say that u is independent of x because ux is 0, and u is independent of y also, and u is only functions of x and y, so that's why it is constant function. And similar argument given for v also. So therefore we can say that u and v are independent of x and y, and therefore u and v are constant on D. So hence you know that f of z is a constant, where c is a complex constant for every z in D. So that completes the proof of this theorem. Let's have the next example. Prove that f of z is equal to sine x cos hyperbolic of y minus I cos x sine hyperbolic of y is nowhere analytic. So to prove this, let us calculate what is the real part of this. The real part of this function is sine x cos hyperbolic of y, and the imaginary part of this is minus cos x sine hyperbolic of y. So if you calculate it, since these functions are contains the trigonometric functions and the hyperbolic functions, first order partial derivatives are exist, so we can calculate them as ux is equal to cos x cos hyperbolic of y. Uy you can calculate as sin x as it is, the derivative of cos hyperbolic of y. So definition of cos hyperbolic of y is e raised to y plus e raised to minus y by 2, and if you can take the derivative of this function with respect to y, it will gives me cos hyperbolic of y. So derivative of cos hyperbolic of y is cos hyperbolic of y, and vx you will have, it is minus minus become plus sin x sine hyperbolic of y, and the derivative of sine hyperbolic of y, the sine hyperbolic of y is e raised to y minus e raised to minus y by 2. So if you differentiate this, it will be plus cos hyperbolic of y. By CR equation what we can say is these two quantities are same and these two quantities are same. So ux is equal to vy will gives you 2 times cos x cos hyperbolic of y is 0, but this will implies cos x is 0 because cos hyperbolic of y is never 0. Because of this, cos hyperbolic of y is e raised to y plus e raised to minus y, and both these functions are positive functions. So that's why this is due to cos hyperbolic of y is non-zero, and cos x will be 0 if x is equal to 2n plus 1 pi by 2 for any n belongs to z, and the other side, that is uy equal to minus vx, will implies 2 times sin x, it has to be sine here, sine hyperbolic of y equal to 0, so that will implies sin x is 0 or sine hyperbolic of y is 0. So that's why this will gives you x is equal to n pi, n belongs to z, or sine hyperbolic of y is 0, that is e raised to y minus e raised to minus y equal to 0. So that will implies e raised to y is equal to e raised to minus y. That will implies e raised to 2y is 1. That will implies y will be 0. So or y is 0. Or we can say now CR equations are satisfied on the set. This intersection with this set. Now what is this above set? It is actually set of all 2n plus 1 pi by 2 plus iy, for y is belongs to r and n belongs to z, intersection with, because the CR equations are ux is equal to vy and uy equal to minus vx, this, that is set of all n pi plus iy, where y belongs to r and n belongs to z. Since this is OR, we can write union x plus I0 because y is 0 where x belongs to. So this is the set we have. Now what is the intersection of these two sets? The intersection of these two sets is only the points where 2n plus 1 pi by 2 is there. So I can say that therefore f of z is differentiable at z is equal to 2n plus 1 pi by 2. But what is the neighborhood of this point? So now what is the situation? Z is this, so it is these are the points where you will have pi by 2, 3 pi by 2, 5 pi by 2 and so on. On this point the function is differentiable. No anywhere else. If you can consider the neighborhood of this point pi by 2, at that neighborhood it is not differentiable. So we can say that f is not analytic anywhere. So that completes the proof of this example, that f is not analytic at any point. Now let's have the next example. If f of z is equal to u plus iy is analytic on D, and its conjugate, that is u minus iy, is also analytic on D, this is given to you, then prove that f is constant D. What is the meaning of this example is saying that if you have a function and its conjugate, both of them are analytic, then the function must be constant. So for that I am considering f of z bar as u of xy plus I v of xy. And what is capital U of xy here? So where capital U of xy is small u of xy and capital V of xy is nothing but the minus of small v of xy. Given that this function f bar is analytic on D, that means it has to be satisfy CR equations. So due to that we can say that it is ux is equal to vy and uy equal to minus vx. So therefore what is ux? Due to this vx is nothing but ux, and due to this vy is minus vy, and on this side ui, that is a derivative of this with respect to y, is a small ui, and on this side you will have minus vx. On the other side what is given to you is also given that f is analytic on D. Since f is analytic, it is of the form u plus iv, so it is also satisfies CR equation. So for that you will have ux is equal to vy and ui equal to minus vx. So if you can see this both equation, this one and this one, so from this two what we can conclude is ux is 0, vy is 0, uy is 0 and vx is 0. Here you will have plus. We can say that f of f dash of z is nothing but the ux plus iv x, and ux is 0 and ui is 0, that means f dash of z is 0 for every z in D. And we have seen the theorem that the derivative is 0, then the function must be constant. So that completes the proof of this result. Let's have the another example. Suppose that f is analytic on D and mode of f of z is a constant, where c is a constant for every z in D, then f is constant. So what is this result tells you? That if f is an analytic function and its modulus is constant, then function must be constant. To solve this example, we just will see that what is mode of z is given as c, so that will imply mode of z square is c square, and mode of z square I can write f of z into f of z bar, which is equal to c square. Now there will be two cases if I consider. So if c is 0, then you will have mode of f of z is 0, that will imply f of z is 0 for every z. So automatically function is constant function, it is a 0 function. If c is non-zero, then you will have this f of z into f of z bar equal to c square. So that will imply f of z I may write down, or f of z bar I may write down at c square upon f of z, because now since c is non-zero, the function is non-zero because its modulus is non-zero. So therefore f of z bar is this, Now since f is analytic, f of z bar is also analytic. Therefore, f of z bar is analytic on D. And what we have is given is f is analytic on D. This is given to you. Our assumption is there. So we have f is analytic and its conjugate is also analytic. So by above example, what we can say is f is constant function. So that completes the solution for this example also. Lastly, I am giving you some examples to solve by yourself. Let us prove that f of z is equal to z raised to 3 by 2 is analytic for all z not equal to 0. This is the first example. The second example, you can prove that z is equal to f of z is equal to z square minus 1 into e power z into e power minus iz is analytic everywhere. That means it is entire function. So these two examples you can solve by yourself. I am giving you as a homework to do yourself. So let us recall what we did in this lecture. We have discussed about the analytic function. Analytic functions are the functions which are differentiable in the some neighborhood of the point z0. So we have all the results of differentiability we can apply here. So necessary and sufficient condition for analyticity, we can say that a function is analytic if and only if the first order partial derivatives of real part and imaginary part are continuous, exist, and they satisfy CR equations. With help of that, we have solved certain examples here, and also we have discussed that the sum of two analytic function is analytic, product of two analytic function is analytic, quotients of two analytic function is analytic, composition of two analytic function is analytic, and at the last we have did two important examples which tells you that if the function is analytic and its conjugate is also analytic, then the function must be constant. If the modulus of the function is constant and the function is analytic, then function itself a constant function. With this, I am stopping here. If you like this video, please press the like button. If you have any comment, suggestion and a question, I am happy to give the answer to them. See you in next video. Till then, bye bye, sayonara.